So we spent a lot of time talking about sine and cosine functions, and now we're going to actually apply those into the more traditional x and y axis plots that you guys are more familiar with. First thing we're going to do is consider the coordinates we're going to draw based on the information we have in our unit circle. So for each coordinate on the x and y axis, the x coordinate is going to be the radian measurements going around the unit circle. So for example, when we say the angles are 0, pi over 6, pi over 4, pi over 3, pi over 2, etc. Now remember, those do have values. So pi, for example, is approximately 3.14. So I'm saying make an x coordinate of 3.14. If you're doing half of pi, then you're somewhere around 1.57. So this coordinate would have an x value of 1.57. And then the y coordinates, since we're talking about sine is based on the y coordinates of the unit circle. The y coordinates will be the y coordinate. So one point we would draw on the graph is the coordinate 0, 0. Another point we would draw on the graph is pi, so go to the right pi, and then don't go up or down at all. That would be another dot we draw on the graph. So we're going to see what this looks like if you plot all of these points into the x and the y axis, focusing on sine of x first. I have a short video that will actually illustrate the unit circle creating the graph. So we'll look at that real quick. Now again, I know it's going very quickly, but if you look at some of these points, and then let me pause this for a second, and compare them to what we had on the last slide, or compare it to a unit circle that you have handy, we said at an angle of pi, the y coordinate is 0. So this dot right here is coming from the theta value, pi, and the y coordinate you see at pi, which is 0. If you look over at half of pi, which is approximately 1.57, you can see that this is x equals 1, x equals 2, so 1.5, it's approximately here. If you look at that pi over 2 angle measurement, the y coordinate on the unit circle is 1. So that's another dot that I'm drawing the graph. Personally, I usually only draw those dots that either hit heights of 0 or hit heights of 1, but technically all the other values are in there as well, like the pi over 6, pi over 4, and pi over 3 angles. So I start off with the height 0 and the height 1 points on the graph, and I just kind of connect them with this wavy motion. So let me keep the graph going here. As the unit circle continues to go around and you're looking at an angle of 3 pi over 2, for example, or going all the way across to an angle of 2 pi, that again hits a y value of 0. So our unit circle, by going around, depending on which terminal line you're looking at, that's what gives you those different marks on the x and the y axis. So here's just a drawn in, filled in version of the sine of x graph. Again, the most important points to me are 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, negative 1, and 2 pi, 0. So I usually just fill those in and then keep making this pattern of waviness going through it. Now, right before the break, we also did a review on the transformation rules. And again, those can be found in the very first section of notes I gave you guys. The very first document I sent out to you, it was called Things You Need to Know for Pre-Calc. And we were talking about some of the transformations like x squared plus 3, meaning to take the graph and then move everything up 3 units. So in this case, we're going to look at how those transformation rules affect something like sine of x. So if I put a number in front, like 2 times sine of x, so pretend a is 2 for a second, it's telling you to take those heights and double them. So instead of hitting a height of 1, which is what we saw in the unit circle, we would hit a height of 2. This has a height of 0. If you multiply by 2, it's still 0. This has a height of negative 1. If you multiply it by 2, that would hit a height of negative 2. And then it goes back to 0. So the first kind of transformation is just doubling the height of your graph. So we call that a vertical stretch. It would be a compression if the number had been something smaller, like if it had been a 1/2. Then I would instead be taking those heights and multiplying them by 1/2, so it would squish the graph or compress it, and you would end up with a shorter sine function. The next rule that I have listed on here is for what happens when you have a negative listed out front of the function. So negative sine of x means you can take those heights and multiply them by negative 1. So basically it flips the graph around, because this has a height of 1 right here, but if you multiply that by the negative out front, it becomes negative 1. Now the heights of 0, 0 times negative 1 is still 0. -1 times -1 would flip up to +1. So for this second case, negative sine of x, this just takes the graph we're looking at and it flips everything upside down to look like this instead. For the next case, we're going to talk about a vertical shift, which is when you take the entire graph and you move it vertically either up or down. So for our example, let's just pretend that this said sine of x plus 1 for a second. So d is equal to 1 in this case. Then for each of the heights you have, for example, this is a y value of 0, I'm going to add 1 to it, which moves the graph up. This one has a height of 1, but I'm adding 1 to the height, so it moves it up to 2. This is 0 plus 1. This height is -1 plus 1. So the effect of sine of x plus 1 takes the entire graph and it shifts everything vertically once. Now, if I had been subtracting 1, then it just would have taken all those heights and taken 1 away and moved it down instead. For the next example, we're going to look at horizontal stretches or compressions. Now the next case is a little bit trickier, and I don't want you guys to confuse it with the vertical stretch. They both deal with you multiplying by a number. The difference is that for a vertical stretch, it's you multiplying out in front of the function. For the horizontal stretch, it's inside of the sine function. It's actually being multiplied by the x value. So make sure you can distinguish between these two cases. They both deal with multiplication. So for multiplying by, let's say, sine of 2x, these are a little bit trickier because what they're going to do is they're going to squish the graph horizontally. So instead of this happening at pi over 2, it's going to happen at pi over 4. It's going to happen twice as fast. Instead of hitting the height of 0 at pi, it's going to hit it at pi over 2. So basically, each of these things that's happening is going to happen in half the distance. So now, sine of 2x, this is a horizontal compression. It's also confusing because it's kind of backwards from what you expect. When you multiply by a number like 2 out front, it doubles the height, so it makes things bigger. On these, it's the other way around. If you have a number like 2, it squishes it. If you have a fraction like 1/2, that's what would have stretched the graph out instead. And we'll look at those in more detail later on too. And then our last case is, again, kind of confusing in the sense that I'm adding a number just like we did for the vertical shift. But instead of having sine of something like pi and then adding 2, now it's sine of the pi over 2 plus 3, or whatever the number is that you're adding or subtracting. So the difference is that now we're adding or subtracting from the x value instead of from the whole function. So when it's inside the parentheses, that's how you can distinguish between these two cases. Since our x-axis isn't labeled with the values of 1, 2, 3, 4, 5, let's make the number that we're adding something like pi over 2 to make this a little bit easier to demonstrate. So pretend c is equal to pi over 2. Then what I'm going to be doing is I'm going to be taking the graph and I'm going to be shifting everything to the left or to the right this amount, pi over 2. Now, what is a little confusing about this is that when you have a plus here, you actually move it to the left. So that often confuses people. So whatever I have at a height of pi over 2, I'm going to move that to the left, that length. Whatever I have at the height of pi, I'm going to move that to the left, a length of pi over 2. So essentially, everything is just going to be moved over to the previous tick mark that I have on this graph. So now my graph ends up looking something like this. And then there'd be one more piece going this way. So those are the transformation rules that you guys have seen before for graphs like x squared, x cubed, square root of x, etc. But now we're applying them to sine, and in a little bit we'll apply them to cosine as well. So let's look at some of the examples we have. So what I always like to do is start off with what the original function looks like before any transformations are applied. And I like to put in some of the most important dots. For example, I like looking at the dot 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. Like I said, I just like to focus on the ones that hit a height of 1 or hit a height of 0 or -1. So going around the graph, you can see that it just kind of keeps making this wave motion. It's kind of like it's bouncing, hits height of 1, bounces down, hits height of -1, bounces up. It just keeps doing that forever in both directions. So now that I have kind of what the skeletal outline of what regular sine of x looks like, it's a lot easier for me to look back and say, okay, from that function, I need to move all of those up vertically a height of 2. Because looking back at the rules we had in the previous slide, when you add or subtract outside of the parentheses, that's what moves the graph up or down that amount. So I'm going to take those dots and move all of them up a height of 2. Now notice I didn't really label anything on my x and y axis here. If you don't label anything on those, I'm going to assume that it's a height of 1, then 2, then 3, then 4, etc. So this is incredibly important, especially if you're planning on making this a height of 1/2 and then 1 and then 1.5, 2. Whatever you're using for your scale, you need to label those so that I can tell if you've done something different to them. So starting with the height of 0, I'm moving it up 2 units. That'll put it here. This dot was at a height of 1. I'm moving it up 2, so it ends up there. In fact, let's even do these in a different color just so it's easier to tell the new ones from the old ones. So height of 2, height of 3. This one comes to a height of 2. This one comes to a height of 1, 2, etc. And it's going to keep bouncing back and forth like this. And then once you get the graph drawn in there, notice all the blue dots are exactly 2 above the red dots. My answer is this part. So that's why I didn't want to actually draw like a dotted line or something in on the red ones, because I'm just using those to kind of guide where my answer is. This is what I would actually be submitting if I were turning this in on a test or something. Here's another quick example. Again, I'm going to start with where the regular dots are, which in this case, since it's still sine of x, we haven't looked at the graph yet. You have a dot at 0, 0, pi over 2, 1. So you'll get faster and faster at this, knowing exactly which dots to fill in here. Now I've actually got a couple transformations being applied on this one. First, I'm going to notice that there's a number out front being multiplied, and then there's another number being subtracted at the end. So if I'm looking at the rules, this is a number out front being multiplied, so I'm stretching the height of the graph, which means I need to multiply those y values by a number, like 2, 3, or 5, whatever they have. Then separately, I'm adding a number or subtracting a number from the end of the function, not in parentheses, but outside of the function. So that's going to move the graph up or down that amount. So let's do these one at a time. First, let's triple the height. So it's going to go from a height of 0, triple that, still 0. Height of 1, if you triple it, goes up to 3. 0 is still 0. Negative 1 times 3 is negative 3. So you can see that the ones on the x-axis aren't moving at all, because 0 times anything is still 0. But the ones that have a height, like a height of 1, goes 3 times as high. Negative 1 goes 3 times as low. So that gives me a rough idea of what 3 times sine of x looks like. But there's one other piece I need to do on this one. I need to take those heights, and then I need to subtract 1 from all of them. So this blue dot is going to move down 1. This dot's going to move down 1. This dot's going to move down 1. So again, I'm just focusing on the blue dots for this step, because the blue dots already show me doing one of the transformations. So I'm taking all the blue heights and moving them down a length of 1. Now if I connect the ones that I did in purple, this is what my 3 times sine of x graph looks like after it's been shifted down a length of 1. So try not to connect all of the other ones as you go through, or do it very lightly with a dotted line or something, because I want to make sure I can tell which one you're saying is your final answer on those. If you have different colors, that helps, as long as you label which one is which. Now, there's a very similar system for graphing cosine of x graphs. It's just that instead of using the y coordinates of the unit circle, we're going to be using the x coordinates of the unit circle. So that's the only difference between our two rules. The x values are still the radian measurements. If you look back at what I wrote before, the x values are the radian measurements. So the x coordinates have not changed. I'm still going to have 0, pi over 6, pi over 4, pi over 3, pi over 2, etc. However, if you're using your unit circle for reference, now the numbers that I'm writing down for the y coordinates of my graph, those are going to be the x coordinates of the unit circle, because that's what cosine is based on. Cosine is based on the x coordinates. So starting at an angle of 0, if you take cosine of 0 or look at the x coordinate at an angle of 0, you see 1. So that's an important one to mark. And then the next one, it happens at pi over 2, you hit a height of 0. And then at pi, you hit a height of negative 1. And then etc. You're going to hit 0 again at 3 pi over 2. And then 2 pi, you hit 1. So the rules for this are very similar. Here's what the graph ends up looking like. It's almost the same as the sine of x1. It's just been shifted over a little bit. So this graph, instead of crossing through the origin, crosses through the point 0, 1. That's the big difference. Sine of x starts through the origin, and then it goes up and then down. So it's everything just kind of shifted over a little bit. So make sure you recognize the difference between those. I always just look at what's happening when x equals 0. If it's touching the origin, if it's at a height of 0, then it should be sine. If it's touching at a height of 1, then it should be cosine. All of our transformation rules are going to be the same. So here's a quick example. Draw the dots for what cosine looks like. So it starts at a height of 1, and then it counts down, and then it bounces back up. And if you're going in this direction, bounces down, and then back up. This graph is doing two things. There's a sign change out front, which is going to flip the direction, and then the 2 is going to stretch the height of the graph. You can actually do both of these transformations at the same time if you want. Just think about what your y value is here. It's a height of 1 times -2 is -2. Height of 0 stays as 0, 0 times -2. -1 times -2 is +2. 0 times -2 is 0, etc. So you can keep going through and applying this same approach. It's flipping our graph upside down and it's stretching it a little bit. So my blue dots that give me the final answer for my graph look something like this. And that is all for the notes today. Thank you.